today I'd like to talk about the extremal number of certain bipartite graphs, and everything I talk about today is joint work with Benny Sudakov. So first of all, what is the extremal number of a graph? So given a graph H, its extremal number x and h is the maximum number of edges in a graph on n vertices that does not contain h as a subgraph. So this is the same definition as was given by Gabor yesterday. So by the classical Erdős-Shimonovich theorem, we know that for every graph H, its extremal number is 1 minus 1 over the chromatic number of H minus 1 plus little o1 times n choose 2. So this formula gives the asymptotic behavior of the extremal function unless H is bipartite graph. So in case H is bipartite graph, this formula gives little o n choose 2, so little o n squared, and we would like to know some stronger result in this case. So in particular, there are not many bipartite graphs when this extremal number is known exactly, and in fact it is one of the most important open problems, or more like projects of graph theory, is to understand these extremal numbers. So one of the first results about the extremal number of bipartite graphs is the celebrated Turan theorem, which tells us that if the bipartite graph is the complete bipartite graph, so in particular this KST is the complete bipartite graph with vertex classes of size S and T, in this case the extremal number is at most some constant times n to the 2 minus 1 over t, where t is the size of the smaller part. However, it is already open whether this theorem, this result is sharp. So the first open question is that what is the extremal number of the balanced complete bipartite graph? So what is the extremal number of KTT? So there is a matching lower bound only in the small cases when t is equals 2 or 3. On the other hand, it's known when the larger part is much larger than the smaller part. So in particular, when S is at least t minus 1 factorial, then this bound is best possible, and there is an algebraic construction showing the tightness of this result by Kollár-Rónyai-Szabó and later Alon-Rónyai-Szabó. So now this was the Turan theorem, and this theorem was greatly generalized in the following manner. So Füredi, and later using the dependent random choice method, it was proved by Alon, Krivelevich, and Sudakov, that if we look at any bipartite graph H, when we only assume that every degree in one of the parts of this bipartite graph is at most t, then we can get the same upper bound. So you can note that this truly generalizes the Turan theorem, because every such complete bipartite graph also satisfies this condition. And again, because we know that in this case this upper bound is sharp, we know that this theorem is also sharp. So in particular, this theorem cannot be improved without knowing more about the structure of this graph H. And also, if we believe that this conjecture is true, then this bound should be sharp for every graph H that contains the complete bipartite graph KTT. So, but then the question arises naturally that what can we say about those bipartite graphs which satisfies this condition but do not contain KTT? So is there any hope maybe that in this case we can improve this result? So this is the question I'm going to investigate the rest of the talk, and this is what I'm going to talk about. And the first result in this direction is a recent result of Kondonin and later in a stronger form by Janzar. So they looked at the first case, the first non-trivial case when t is equals 2. In this case, they prove that if we look at a graph where every degree in one of the parts is at most 2, and we also assume that this graph do not contain k22, then the previous theorem can be improved. They prove that there exists some delta which depends only on this bipartite graph H, such that the extremal number of this bipartite graph is at most n to the 3/2 minus delta. So let me remark that we have these conditions which might seem a little artificial. But in particular, these kind of graphs appear naturally. So these graphs can be also viewed as just subdivisions of graphs. So what's a subdivision of graph? So given a graph, we can subdivide every edge by a new vertex by introducing a new vertex which cuts this edge into 2 parts. Or in other words, you can define the subdivision of a graph or even a hypergraph in a way such that it is a bipartite graph whose vertex classes correspond to the vertex set and edge set of this graph, and then we connect an edge with a vertex if this edge contains the vertex. Now, because every edge contains 2 vertices, these graphs satisfy the property that every degree in one of the parts is 2, and also because we are talking about graphs and not multigraphs, this graph is also going to be k2 free. So in particular, this theorem could be reformulated that if we have a subdivision of a graph, then its extremal number is at most n to the 3/2 minus some positive constant delta. So this was about the case t equals 2. So what about okay. Oh, it's very close to dying, but let's go with this. So for larger t, it is not known whether this result can be improved, and in particular, this conjecture was proposed by Conlon and Lee. So they proposed the conjecture that if we assume that we have a bipartite graph where every degree in one of the parts is at most t, and it avoids ktt, then again we can improve this upper bound of Furedi and Alon-Krivalevich-Sudakov. Okay, so what's known about this general conjecture? So one known result is from Conlon, Janzer, and Lee, who proved that if we consider a bipartite graph where every degree on one of the parts is t, so the usual condition, but instead of forbidding ktt, we forbid k22, which is a much stronger condition, then we get that the extremal number is little o of this n to the 2 minus 1 over t. So in this case, they have this stronger condition of forbidding k22, and also they couldn't get this minus delta improvement in the exponent. So this is really just a little o improvement, and this little o is really little o, so it's even worse than log n or log star n. It's a very small improvement. But at least we know that there is hope that the general thing might be true. So let me remark that this result can be also formulated in the language of subdivisions. So the bipartite graphs satisfying these conditions are actually just subgraphs of subdivisions of T-uniform linear hypergraphs. So what's a linear hypergraph is just a hypergraph in which any 2 hyperedges intersect in at most 1 point. And because it seems that this question is really hard, they proposed the relaxation of the original conjecture. So they just proposed this conjecture that if we look at a subdivision of any T-uniform hypergraph, then we also get this little o improvement. So note that again, if we have the subdivision of a T-uniform hypergraph, that's a bipartite graph where every vertex in one of the parts is at most t. And also these such graphs avoid k2t. So they do not avoid k2t, but the stronger condition that they avoid k2t. So this was more or less all the results that are known. So, but now let me show you what we managed to prove. So we managed to prove something that's much stronger than this conjecture, but slightly weaker than the original conjecture. So what we managed to prove is that, so we managed to prove the original conjecture, but instead of getting this minus delta improvement, we only managed to get this little o improvement. So if we are given a bipartite graph where every degree is at most t1 of the parts, and this graph avoids ktt, then we truly get that the result of Alon-Krivulevich-Sudakov and Führer is not sharp and can be improved. And the proof of this result is quite short, so I think the remaining time should be enough to give you a rough sketch of our ideas and what we are doing. So I'm only going to cheat at certain technical details. So let's see the proof of this. So first of all, instead of looking at a general graph H like this, we are going to look at a universal graph H, which contains all such graphs H. So what we are going to look, let me draw. So this is going to be our graph H. We have two vertex classes where x is of size r, and it has the property that for every t tuple of vertices, so every t tuple of vertices in X, there are exactly t minus 1 common neighbors. So here, and for distinct hyperedges, these t minus 1 vertices are also distinct. So in particular, we get that y will have size exactly t minus 1 times r choose t. But this bound is not important. So now if we choose r to be sufficiently large, then it will contain our original graph H. So we can only, so it is enough to only consider graphs H like this. So this is H. And now what we are going to do, we are going to look at a host graph G, and we want to show that if G has at least some epsilon and to the 2 minus 1 over t edges, then we can find a copy of our graph H when n is sufficiently large. So this is going to be our plan. Now, one usual idea how proofs about the extremal number of bipartite graphs start is that we would also like that Rg is bipartite. So this helps a little bit. And then we can also assume that G is a symmetric bipartite graph. So because if we just take a random partition of the vertices of T in G into two equal parts, then we can still keep at least half of the edges. So we do not lose much, and then we can assume that G is bipartite. So this is the usual first step. But our new idea already comes here, because instead of doing this, what we do is this slightly strange setup. So instead of finding a symmetric bipartite graph in G, we want to find a very asymmetric bipartite graph. So what we are going to do is we are going to find a large bipartite subgraph G prime of G, which has this following form. So this is going to be G prime. So it will have two vertex classes, U and V, such that the size of U is going to be roughly some large constant times n to the 1 minus 1 over t. And V is going to have size some constant times n, so let's say n over 2, where this 1 over 2 is not important. So this is going to be our host graph. And if we select our U and V randomly, then we can also guarantee that we can keep a lot of edges. So we can So we can also assume that G prime still has at least epsilon prime and to the 2 minus 2 over t edges. So why is that? Where epsilon prime is some constant. So why is that? Because if we pick a random subset of size this, then we can still keep n to the minus 1 over t proportion of the edges. So that's why we have 2 over t here instead of 1 over t. And finally, I have this technical condition that the maximum degree of G prime is not too large. But this is really just a technical thing to assume. And I'm only going to use it at the very end. So now, here is our new host graph G prime. I forgot about G completely. And now my plan is to embed H into G prime such that I embed X into U and Y into V. Okay. And now what we are going to do, we are going to define a T-uniform hypergraph on U such that a T-tuple forms an edge. So here, a T-tuple is an edge in this hypergraph if it has at least T minus 1 common neighbors. So if this okay. So now what should be our plan roughly? So roughly we would like to find a clique of size R, the size of X, in this T-uniform hypergraph. So because then in this clique, we could view this clique as a copy of X, and then we try to find the rest of the vertices in Y. So, but of course, just finding a clique is not enough, because it might be that in this clique there are two hyperedges whose neighborhoods coincide a lot, and then we want T minus 1 distinct vertices for each of these hyperedges. So in some way, we need to guarantee that for every edge in this clique, we can find these distinct vertices. So now what we are going to do is we are going to distinguish hyperedges based on how many common neighbors they have. So we will distinguish so-called heavy and light edges. So I will use colors for this. I will use red and blue edges. So here, an edge is going to be red if it not only has at least T minus 1 neighbors, but also has at least this T minus 1 RT common neighbors, which this number should be familiar, because this is the size of Y. And then the rest of the edges are going to be blue. So blue edges has still at least T minus 1 common neighbors, but they have at most these many common neighbors. So now we have this nice two coloring on our hypergraph. So why does it help us? So first notice that if we find a red clique of size R, then we are already done. So why is that? So let's say we found some red clique of size R here. Then it means that every hyperedge inside must have at least these many common neighbors. But then we can just greedily pick T minus 1 elements of each of these common neighbors, and we can do this in a way so that these T minus 1 element sets are disjoint. So then we found our vertices Y, and we are done. So in the rest of the proof, we can assume that H does not contain a red clique of size R. But then this already suggests some kind of Ramsey theory. So Ramsey's theorem tells us that there exists some large constant R, where constant means does not depend on n, such that if we consider any two coloring of the T-uniform hypergraph on capital R vertices, then it contains either a red clique then it contains a monochromatic clique of size little r. So in particular, this means that if we if we fix a set of, let's say, size exactly, so if we fix a set of size t minus 1 mv and we look at its neighborhood, so now we look at its neighborhood, and this neighborhood is large. In particular, it's larger than this capital R. Then this neighborhood contains either a red clique of size R or a blue clique of size R. But we know that there are no red cliques, so it will contain a blue clique of size R. So, but why does this help us? So remember here that here I choose u to be some large constant times n to the 1 minus 1 over t. So, but now what is this large constant? I can choose this large constant so that it's going to be true. It's just some calculations on convexity inequalities. So this is just some technical stuff. So I can choose this, say it large enough so that in average, every t minus 1 tuple in V will have a neighborhood that's larger than R, or even larger than 2R. It's a little helpful. So in average, because of the reasons I said before, we get that in average, every neighborhood of size t minus 1 will contain a blue clique of size R. So in particular, this gives us the size of this hypergraph to the t cliques of size t. So we have the size of we choose t minus 1 tuples in V, and because we chose our numbers that way, this is at least some constant times the size of u to the t. But also notice one more thing. So I claim that there cannot be too much overlap between the blue cliques. So in particular, any hyperedge in this graph, in this hypergraph H, can be contained in at most a constant many of the neighborhood of these t minus 1 tuples. So why is this true? Because remember that an edge was blue if it had a small neighborhood, if its neighborhood had size at most this number, which is a constant. So the number of t minus 1 tuples whose neighborhood contains a particular blue edge is just this number, choose t minus 1 at most, which is still just a large constant. It's independent of n. But I can reformulate this in another way. I can also say this sentence as that if I remove a hyperedge from my graph H, it can destroy at most a constant number of these blue cliques. So in particular, if I want to destroy every blue clique, I have to remove at least a constant times the size of u to the t edges. So, but why does this help us, or what does this give us? So now here I'm going to use a deep result from hypergraph theory, which is called the hypergraph removal lemma of Nagel, Rödl, and Schacht, and Gowers. So the hypergraph removal lemma tells me that if this is the situation, then this implies that I must have not only these many cliques of size R, but I must have actually the size of H to the R cliques of size R. So maybe this hypergraph removal lemma is not that known, so maybe let me say a few words. So the hypergraph removal lemma tells you that if you look at a hypergraph and you consider the copies of some other hypergraph in this hypergraph, and you find that you have to remove at least a positive density of the hyperedges to destroy every copy of this hypergraph, then this implies that you also have a positive density of your hypergraphs. So this is the hypergraph removal lemma, and so we get these many cliques. So now we are almost done. So what we want to do is we want to find one of these cliques such that I can embed H in a way that I embed X into that clique of size R. So now what we are going to show, we are going to do some counting where we are going to count some bad cliques of size R. So we are going to count those bad cliques where this embedding is not possible. And then we will find that the number of these bad cliques must be much smaller than this number. So now this is the end of the proof. So how can we count these bad cliques? So let's just fix a clique of size R in U. And let's suppose that we cannot embed H in our graph G prime in a way that X is embedded into this clique C. Then this must mean that because every hyperedge in C has at least t minus 1 common neighbors, so the only problem when these common neighborhoods intersect. So if all these common neighborhoods are disjoint, then I'm happy, I'm done. So the only problem if there are two hyperedges whose neighborhood that have a common neighborhood have a non-empty intersection. But in other words, you can say this by picking a vertex in this common neighborhood X, then the neighborhood of this vertex X, so maybe, so here, then you can find the vertex X such that its neighborhood, okay, so maybe the neighborhood is larger. So this neighborhood intersects our clique, say this clique, in at least t plus 1 elements. So why is that? Because the neighborhood of X contains the union of f and f prime, and these are distinct hyperedges of size t, so their union has size at least t plus 1. So this gives us this intersection is at least t plus 1. But then we can just count these bad R cliques by counting them from the vertices in V. So by summing up from every vertex in V. So in particular, so summing up for all X and V, we have that this intersection of size t plus 1, we can choose this at most size, the degree of X, choose t plus 1 times, and we can choose the rest of the R minus t minus 1 vertices in our clique in at most u to the R minus t minus 1 ways. And then we, by just simple calculations, show that this number is truly little o of u to the R, so this is much less than the total number of cliques of size R. So in conclusion, the number of bad cliques is much less than the number of cliques, so there must be a clique where we can embed H in the desired manner. And this is the end of my proof, and also this is the end of my talk, so thank you for your attention.